Right, so let's continue. So we look at powers. Let's begin. Let a be greater than 0. We can ask, um, can we define powers a power r, where r is rational? So let a be a positive real. Can we define powers a power r, where a is rational? So this is a difficult question to deal with directly. So let's consider, let a be greater than 0. Let n be a positive integer. Now we can ask, can we define the fractional power? So can we define the powers a power r, where r is rational? We are asking the simpler question. Let a be a positive real, let n be a positive integer. Can we define the fractional power a power 1 by n? Can we define what this a power 1 by n can be? Can we define a quantity a power 1 by n? So let's see. We want a power 1 by n to satisfy. So this is what we want. We want to be able to take n copies of a power 1 by n, and multiplying them, we want them to be giving this. We want a power x plus y to be a power x plus a power y. So we want this equation to hold. Hence we want a power 1 by n, when multiplied by itself n times, it should give, so n times is better. So when we multiply a power 1 by itself n times, it should give back a. So this is what we want. This suggests the definition. So we define nth roots. So let a be greater than 0. Let n be a positive integer or nth root. Okay, let n be a positive integer. Then the unique positive real box such that box power n is equal to a is called the nth root a power 1 by n. So the unique positive real box such that a box power n is a is called a power 1 by n. So we can ask, does a power 1 by n always exist? Whenever we define some quantity like nth root or anything, any quantity, we should immediately ask, does it always exist? Let a be greater than 0. Let n be a positive integer. So does this quantity a power 1 by n we defined above, does a power 1 by n exist? If a is a positive real and n is a positive integer, does a power 1 by n exist? So it turns out it's a theorem in real analysis, but we will not prove it here. So this is about nth root. Let a be a positive real. Let n be a positive integer. Then a power 1 by n exists. So I need not write this again. So then a power 1 by n exists. We defined a power 1 by n above. This is the definition of a power 1 by n for any positive real a and positive integer n. So there's this theorem that if a is a positive real and n is a positive integer, there does exist a unique real positive real box such that box power n is a, that is there does exist a power 1 by n. So this is a theorem, will not prove it, so I'll just mention what the proof entails. So proof is later. It uses an axiom which we did not discuss, uses the supremum axiom, is uses the supremum axiom of real numbers. So we'll not prove it now. And so nth roots exist, a power 1 by n exist. So there's a notational thing. Let a be greater than 0. We write, so a power half, we write a power half as, for some reason, square like this. So under root of a. Okay, so square this symbol, this kind of a under some root kind of thing, that just means a power half. Okay, so we have defined a power 1 by n, and it turns out a power 1 by n exists for all positive, for every positive a and positive integer n. Now, so once we know that these nth roots exist, we can ask another question. So now that we know that nth roots exist, let's see, let a be greater than 0, let n be a positive integer. Now we can ask, can we express ab power 1 by n, the nth root of ab, in terms of nth root of a and nth root of b? Can we express the nth root of the product in terms of the nth roots of the individual expression, individual quantities? So here's the theorem, or here's an observation. Nth root of product so let a be positive reals, let n be a positive integer, then this quantity ab power 1 by n, the nth root of ab is just nth root of a times nth root of b. So finding nth root of a product of two real numbers is easy if we know the two positive real numbers is easy if we know the nth roots of the individual numbers. So we just multiply the nth roots. Let's see the proof. So note that proof is simple. Note that a power 1 by n times b power 1 by n, if we take this n times, if we multiply with itself n times, then we would get a power 1 by n, you'd get a power 1 by n multiplied by itself n times, and b power 1 by n multiplied with itself n times. So product of these two quantities, which is just ab. Hence a power 1 by n times b power 1 by n acts as the nth root of, so the nth power of a power 1 by n and b power 1 by n, the nth power of this quantity is ab. Hence a power 1 by n, b power 1 by n acts as nth root of ab. So hence the unique positive real such that whose nth power is ab is just a power 1 by n times b power 1 by n. Right. So this is a basic observation about nth roots of nth root of product. And now we can get back to the original question. So what was the original question? let a be greater than 0. The original question was, can we define powers? So we have defined powers a power 1 by n for any positive real a. Can we define powers a power r, where r is rational? This was the original question, which we partially answered by defining 1 by nth powers or nth roots. So can we define a power r where r is rational? So let's consider this question. Let's fix a representation of r here, and then we'll later show that it's independent of representations and all those things. So let a be greater than 0, let m and be integers, and let's say the denominator n is greater than 0. Now we can ask this question, more specific question. Can we defined a power 1 by n, can we define a power m by n? Can we extend the definition of a power 1 by n to a power m by n, where m and n are integers and n is greater than 0? So we'll answer this. So recall the definition of m by n. The definition of a power 1 m by n is in some ways similar to the definition of m by n. So let's see how it is similar to the definition of m by n. So how do we define m by n? Let m and be integers and n is greater than 0. Then the unique real box such that, so if you add n time box to itself n times, that is n times box, this is equal to m. The unique real box such that n times box is equal to m is called m by n, right? So this is the definition of m by n. This suggests the definition of a power m by n. So here is the definition of a power m by n. Let a be greater than 0, let m and be integers, n is greater than 0. We'll mimic the definition of m by n, but we'll take positive reals. The unique positive real box such that, so instead of addition we'll take multiplication. Box multiplied with itself n times is giving a power m, so is called a power m by n. So this is the main definition that we are taking. A power m by n, we are defining like we defined m by n, the unique positive real box such that box power n is a power m is called a power m by n. This is like the definition of m by n, right? So right, so does the above, does the definition a power m by n agree with the previous definition of a power 1 by n? So it agrees, right? So setting m equals 1, we are just asking this is the definition of the nth root of a, the unique positive real box such that box power n is a power 1, that is called a power 1 by n. So it does agree with the definition of a power 1 by n, the nth root definition we saw. Another question we should ask is, after seeing the definition, we should ask whether the definition is, if we are extending a definition, here we are extending the definition of a power 1 by n. So we are extending this definition of a power 1 by n. Here we can also write, it's the definition of a power 1 by n. So we are extending the definition of a power 1 by n to a power m by n. Whenever we are extending a definition, we should ask, is the definition consistent with the previous smaller version of the definition? So if it's consistent, it's good, and we should be asking another question. Whenever we define something, does it exist? So let a be greater than 0. So the existence part will be clear once we rewrite this. Hence, so definition a power m by n, it's a unique positive real box such that box power n is a power m. So let a be greater than 0, let m n be integers, n greater than 0. Then so a power m by n is defined to be, it's the nth root of a power m, if we look at the definition. The unique positive real box such that box power n is a power m. It's just the same as saying the unique positive real box such that box power n is a power m is just the nth root of a power m, right? So we are defining a power m by n as the nth root of a power m. It's quite simple. So in terms of nth roots, we do get the definition of a power m by n. So even this question, does the definition of a power m by n agree with the previous definition of a power 1 by n? Even this becomes very trivial once we rewrite the definition. So I'll write it here itself. Hence, we can rewrite the definition of a power m by n as, so this is the definition, let a be greater than 0, let mn be integers n greater than 0, then a power m by n is the nth root of a power m, and this exists because nth roots always exist. We discussed that nth root of a positive number always exists. So this is the key theorem. We are using the existence of nth roots, which we are not proving. Every positive real has an nth root. We are using this important result. Then let's see. So in terms of nth roots, we are just defining a power m by n to be the nth root of a power m. The above definition, which is similar to the definition of m by n, can be rewritten as a power m by n is just the nth root of a power m. Okay, so, and now we can ask, so a power m by n is just, so instead of putting the box on the entire thing, we can focus on the essential thing. The essential thing is just that a power m by n is this, the nth root, a power m by n is just the nth root of a power m. So now we can ask nth root of a power m power 1 by n, and the nth roots are defined as above, like the unique positive real such that box power n is a, that is the nth root of a positive real a, right? So we have defined a power m by n for any positive real a. Now the form of this expression suggests a question. Let a be greater than 0. Let m and be integers, n greater than 0. Is a power m by n also equal to the mth power of the nth root of a? So is this relation also true? We know that a power m by n is by definition a power m power 1 by n, but do we also have that a power m by n is a power 1 by n power m? So here's an observation. Here's an observation. So this is just that a power m by n is in fact a power or I'll write it here. A power m by n is also a power 1 by n power m. So this is the observation. And let's see. Let a be a positive real. Let mn be integers. N is greater than 0. Then the claim is a power m by n is a power 1 by n power m. This is the claim. So we'll look at the proof. So consider this quantity box equals a power 1 by n power m. We are to show, to prove this relation, we are to show. So to show, so box is a power m by n, that is, so we are to show box power, so we are to show that box power n is equal to a power m. Let's see. So note that box power n is equal to, so a power 1 by n power m, right? So we are taking this quantity power n. So this is just a power 1 by n power m, a power 1 by n power m. We're taking it n times. So we can instead look at it this way, that we are taking a power 1 by n, a power 1 by n n times, and that we are taking power m, right? And sorry, instead of doing all that, how many a power 1 by n copies do we have? So a power 1 by n, a power 1 by n, you have, so the m copies you are having n times, mn times, right? So we are having a power 1 by n mn times. Now we can rewrite these mn times as a power 1 by n. So these you can take n times, and by n times. So these copies you can take m times, right? So a power 1 by n taken mn times. Box power n is essentially a power 1 by n taken mn times. So we can rewrite that as this, and hence this is just a taken m times, right? So this is just a power m. Hence box power n is equal to a power m as needed. We showed that box acts as the nth root of a power m. So box was considered box is equal to a power 1 by n power m. We showed that box power n is a power m. Hence box, which is just a power 1 by n power m, this acts as the nth root m by nth power of a, right? So we know that a power m by n. So to summarize, we know that let a be a positive real, let m and be integers, n greater than 0, then so a power m by n, which is defined to be the nth root of a power m, we saw this is the definition, so it can also be written as the mth root of a power 1 by n. So this is the summary. Or I'll just highlight the equation which is of most relevance. So this includes both the definition and the above result, that a power m by n is a power 1 by n power m. So this is how we define a power m by n, where a is a positive real and m and n are integers and n is positive. So we'll continue with the discussion. So that's all for this part. See you in the next part.